hopefully it's okay for you until here. So we will cover about 6, 7, 8, 9, 10. Right. So today we're going to talk about neurulations. So this is the process that marking the, or we call it the auto coordination thinking, and basically it's between it will somehow enhance our body to process requirement. Sitting, Fatima, there's one electricity there, there's two electricity there. You want to see? Okay. There. Okay. Now, what is the neurulation? So neurulation is basically what I'm going to explain about the outline of neurulations and certain characteristics of each and everything of every person. So basically, this is the general information about neurulation. So it was derived from the outer layer, the ectoderm. So the ectoderm basically only a special ectoderm will become the neuron. So this is what we call the neuroectoderm. The neuroectoderm is basically by default is actually undifferentiated or undifferentiated structures. So the surface ectoderm will be derived from your skin, nails, hair, and so on and so forth. But the neuroectoderm is going to form the nervous systems. But when we talk about nervous systems, there are all nervous systems. You know that you have the central nervous system, and then you have the peripheral nervous system, right? So peripheral nervous system is whatever that branches out from your central nervous system. Then you're going to have sympathetic, parasympathetic nerve, and so on and so forth, right? Okay. So the neural it was started with the formation of neural tubes. The main target is to form the neural tube, and then from the neural tube, what we call it the collateral or byproduct or side product, byproduct of the process of neural tube. Then you're going to have what we call it the clusters of neuron, we call it the neural crest. So these neural crests later on, neural tube will become the central nervous systems, and then the neural crests become the peripheral nervous system (PNS). So this is basically what we call the general pathway of what happens in organism. So in human, basically the formations of neural, once you have the ectoderm basically you can get it through the gastrations. So when gastration is basically, we talk about neurulation. Neurulation is similar or simultaneous process. Once you produce the gastration, you not only get the ectoderm and mesoderm or endoderm, but you're also going to find that it will some sort of delay later on, then you will get neurulation. So basically, it was almost simultaneous process happened with the gasturations. And then what happens that all these things, they shall be completed within 4 weeks. Okay? Within 4 weeks 4 by week 4 of the embryo. So in the summary, what we're going to get in neurulation is that what we want is that as I said, it will only involve one particular type of cell, which is a neural ectoderm. Okay? So neural ectoderm basically it will form through a process of reshaping, morphogenesis. Then you have the process of columnarization, where you try to what we call it shaping the cells. And through the process you can form neural plates. From the neural plates you can start to have what we call neural fold, the neural groove. basically you simultaneously you get a neural groove in the middle and a fold at the edge of the plate. Then you can from the fold you can have a neural tube. Okay, so a neural tube, from neural tube you can have brains, stem, and so on and so forth. That is the general what's going to happen, right? So of course there are always some modifications, some deviations. For example, not all neural ectoderm or ED will form neural tube. Okay, in form of how to say in a process of involving the neural fold and so on, like formation like this. So sometimes you have some modifications, later on you will explain. Right. So this is what in summary. So the summary also, well, you can see here that what we're going to focus now is somewhere at within this week. So if you remember that last week in one of in our lecture, I'm talking about the formations of the respiration, right? And then I mentioned about the Hansen knot. Okay? So the Hansen knot where you start to have the primitive straight. Okay? The primitive straight basically, so what happens is that through a process of proliferation means that you increase the numbers of cells with high speed and then it proliferation and then you have some sort of migration. So the migration basically you form a primitive straight. The migrations of what? Of the order cells. So this is what we call it the ectoderm cells. And then it moves to inside and then replace the hypoblast. Replace the hypoblast layer through process of ingression. Remember? Ingressions. And then it forms a new layer endoderm. Right? So underneath the endoderm there are special structures known as notochord. So this notochord basically this is the one that we determine where when to start the process of neural relations, right? So as I said, once you have the formations, and then what happens is that this notochord basically it is overlay on the ectoderm, and then this is what we call it is send signal known as what we call it the sonic gene or SH genes, and then this SH will induce the formations, the transformations of neural ectoderm to become neural tape and so on. All those processes basically it was started or it was influenced by the notochord. Okay, right. So how initially it was formed. It was started when the primitive straight. Once you have a primitive straight and then a primitive straight touch the special structures known as the node. Okay, right. Right. So this is a summary of what. So if you look at here, basically you have this part is the head, this one is the tail. If you can see at the end of the day 23, then you can see that this is you start to have some sort of like opening somewhere here and then opening somewhere this one. So a little bit delay. What happened is that all the process started somewhere at the neck region area, and then you have this one is not being closed, completely closed. So later on something will happen on that structures. Okay, right. So this is what we call the neural plate. So as I say, a neural plate will be formed the EN ectodermal neuron basically is undetermined cells. It's a special cells. It's not as what people ordinary ectoderm, because ordinary ectoderm we form skin, hair, and so on. So whatever that you get, what you see on your body now, basically, it was formed from the ordinary ectoderm. The special ectoderm, the ectodermal neuron, basically, it will be influenced by the notochord by activating what we call the sonic gene, SH here, and then it will induce all these things to form through the neural inductions to form like plane structures. It started somewhere at a node area and then form a structure like this, like a spade structure, where you have the largest area somewhere at the back of your region, somewhere here, and then the smaller somewhere in the power area. So in the beginning, when in the beginning of study on the new relations, basically what happened is that it was thought that you have a non-part, and through SH genes, it will influence the EN and the neuron to become what we call it the neuroplates. Okay, neuroplates. So this is one, and then a neuroplate, and then the neurofold, and then become a neuron. Okay, right. So this is what it was thought that it was not activated by SHs, the neuroplate then become ordinary ecto, and then it become whatever the skin, etc., etc. So this is what in early studies of the things, they become what we call is if it's not activated by the SH gene or not of part, the ectodermal ectodermal neuron will become what we call it the surface ectoderma, and they become the skin and so on and so forth. Right. So that was thought at the early of the studies, but later on we realized that through the process we realized that actually the SHH is basically just a key to turn on the process. If it's not been turned on, actually it will not turn into this one. Actually, by default, the ectoderm will become the neuron. Okay, by default. If what happens is that through the process ages, so actually what happens is non-cord has sent a signal to the EN, so that EN will go through process here and then. So meaning that what happens is that it causes some sort of delay in the formations. If it's not been what we call it, it's not been controlled by non-cord, what happens is that the ectodermal neuron completely will become a neuron process. So instead of they are forming a hollow structure like this, like a donut, now they become a compact structure without any lumen or any hollow in the structures. So basically it will become like this. It just falls a rule of right. So this is what happened. So currently, it was known that actually it will form, it will send a lot of signals through the SH. It started with SH and then form relay through what we call it the protein inhibitions. Okay, protein inhibitions. Then that's why it calls it. So why they need a delay? Where do they need a delay? So what happens is that the delay is basically it will allow sometimes for neural ectoderm to form a neuroplate. Why is it important to have a neuroplate? Because basically what we want is the spaceship like this. So you want something that big. So what happens is that it will help sometimes, it will assist in the formations of the brain later on in the process. So what happens is that if you are not controlling the delay, what you only have is a structure like this. Similar structure like the one, the signs that you have in the cover area. Okay? So if you have that one, so the problem is that you're going to have difficulties in order to form the brain. Because remember, this one, this neat area will become whatever the encephalon or the encephalon or the cephalon or the brain area. Okay? Right. So that's why we need a right. So we know that. So now we with the ectoderm, and then this it was started with the notochord activation of the HHG. Now, so what it need to do in order to form a plate, or what we call a neural plate, is basically they have to go through a process what we call the columnarization. A columnarization is basically it will happen in somewhere in the calculations. So what happens is that you want to change the shape of cell without change the mass of the cell. Now the numbers of cells will be, you have good and good numbers of cells. But what we think is that you're going to have a shape. You produce the shape, okay, without having produce mass. We need an increase in the mass. So from the structure like this, now you have a range. So basically, why they will have what the target of the process is to produce these special structures. We call it the wedge structures. Okay, the wedges. So what happens is that basically you have a smaller point and the other point somewhere. This is the shape, and then this is the shape of plates. And what happens then from the plate they need to form wedges. So once you have the wedges, basically the same numbers of cells, now you start to form like a curve structure by nature. Okay? By nature is a form of curve structures. So the process of colonization basically it puts a stress to the cells. So it was shown if you look at here, the degree of colonization that happens in the groups of neurons. Alright? So if you remember if you remember the previous diagram, you have the bigger and then smaller overhead. So this is the outer area. So the bigger one meaning that, as I said, it changed the shape in that domain. So meaning that it become like the roti canai one, right? You stretch, but it's not, you stretch to the maximum without causing any damage to the systems. So basically, if you look at in terms of degree of stress, somewhere at the region, or somewhere here, and to the back, it's basically up to the 9 scale, 1 of 10. Right? So it shows why you need to have a colonization. Because colonization now we try to form a plate. You just imagine you stress the floor to have a roti canai to the extent. But if you notice that the outskirt of the outside the edge of your roti canai, now you have a little bit thicker structures, right? So this is what we call the leaf structures. Right? So what happens is that here just to show you the difference between cells that go through process colonizations and the normal cells, the outside. So they be structured. Okay? Right. So that's this one. Now, once you have that one, then you start to form what we call it a neural tube. So inside the neural tube, but bear in mind that as I mentioned earlier, so the target of neuration is to form a neuration tube. So then a neuration tube, later on, it will form what we call it the central nervous system. When the central so the central nervous system, but the neural tracks you look at here. So at the border plate, somewhere here, you get there, in the diagram, light blue area now, when you start to close the light blue area now, it becomes what we call it the neural tracks. So this is become a neural tracks. Because of its still obtain what we call it the neural property. So might as well we use that property to become the extension of the central nervous system. Now this one is going to become your central nervous system. So this one becomes the peripheral nervous systems. Whatever that come out from the center. So then it's either you have all those parasympathetic or sympathetic nerve and so on. No? Have you heard sympathetic, right? So it's always good contradict each other, right? So that one will become almost from the neural crest. So meaning that in what happens is that basically a neural crest, the process of neural relations does not need to have a neural crest. Okay? It no need. So that's why it can be limited from the system. You only require this size. So not the one or the neural board, because this one is too thick. Then the system will become neural. So basically this one is a byproduct. So because of the product, because of it still have neural properties, then might as well we use that one to form extension of central nervous systems. Right. When we talk about neural tube, there are two types of neural tube. So when we talk about neural tube, there are two types of neural relations. Now we start to have a primary neural relations, and then we have a secondary neural relations. So secondary or primary neural relations, neural tube basically you have two types of neural tube. One we call it the cranial crest, meaning that what happens that with the tube that form inside your cranium or your head, and then a caudal neural crest, which is that was the one that happened in the end of your central nervous systems. Now the cranium basically it will use the primary relations. The cranium will be primary, but the caudal will use a secondary relations. Okay, right. So that is what you're going to have in the process. Okay. Now, and is any problem? Okay. Now, so when you start to have all those things, so this is basically what you will do, right? Right. So what you need to have is that when you talk about this one, is the existence of the crest. Okay. Now this is so if you look at here, is you will start to have a neuroform and neuroformation. So what we have is some opening that form from the neural base. So you start to have a form where you will start inside somewhere area your neck region. Your neck region will close and midway along the neural groove. So this is the neural groove. Basically, underneath the neural groove, there is structures of neuron. So in human, for example, in birth, so let's say you have a notochord cord, and then all the process of folding is happen when they go in the place start touch the notochord. When it touch the notochord, meaning that it reach to the maximum position. So because notochord basically is embedded in the system. The cross cut of the cells basically you start to have play, and then it's open up, stretch, polarization up until they will touch the notochord. Once you touch the notochord, then they will notochord send signal. It means that they activate the SH gene, and then it sends signal so that now you have to start to fold. We start to fold somewhere at the back, at the neck. One is neck region. So this is if you refer to this one, this is where the most stretched area. Okay, if you look at now about 9, so this is the most. So this is area where you're going to have that because of it's to the max, right? So what happens is that they will start somewhere there and then move from the midway to the upper and the lower regions. You start to close the middles and then start to close. And then once at the end of the process that you have these two opening areas. So at the primary and the outer regions. if you refer to the colonization map, you can see that the bottom part is have a lower stratigraphy, something like that. So meaning that what happened is that area is still thick. Okay, that's really thick. So that's why if you have a thick area, then it's impossible for you to fold it. So that's why you still have a thick there. Okay, right. So the existence of the opening somewhere here is going to be somehow, if you come across spina bifida, basically is where what we call it, the informations of the deformations of neuron that some maybe have opening at this outer area. So meaning that the nerve is exposed. So that condition is called a spina. Or unnecessarily meaning that what we call it, that the anterior humerus or somewhere here is not close. In this region, it's not close. So usually the chances is to have this one is higher than this one. Okay, right. So what is actually the primary innovations and what is the secondary innovations? So this is what we call it the primary innovations. Primary innovations basically you have a normal ordinary process when you start from the plain area, from the plain structures, and then you start to form the whole structure. So this one basically it was as I said, it was started when the mid area, the neural root start to touch the neuron. So what is that the cell that touch the neuron now become a bit thicker. Now it forms expression structure known as the hinge process. Now it becomes the medial hinge point. Hinge point is basically a pivot structure where you have, if you just have a plane like that, so you're going to have a problem. So what happens is that this area that becomes, if you have the structure that you have a pivot, so basically you have a straight structure. So in order to form a structure like this is impossible. So what happens is that some of it will be hold, it will stick to notochord and then become a hinge, or you call the pivot point, right? What is the pivot point in your body, for example? Like your leg or your knee is a pivot point, right? So this is area where you start to have a thicker cells. So this thicker cell basically is not thicker cell, but it's most of it is a wedges shape. When you have the natural wedges shape, basically by nature they start to form. You try to it somehow it push the system to forward. Right. So then we will talk about the forward. Then what happens is that underneath of these structures, you can see that what we call is the squamous epidermis start to push all these structures. So the process of push is basically what is a multi plate. So what happens is that because of the wedges shape here, okay, you have the wedges shape somewhere here, and then you have what we call is the columnar structure and the formations of new cells somewhere here. It push to the top, and then this one is basically push that way. Right. So when you have that structures, when you have these positions, so basically you have one is on this. Now basically what you have is that you have this one because of the natural shape of the hinges, and then it's actually because of the squamous epidermis. Then what happens is that basically it lifts the structures. It lifts it. But what happens is that if it just depends on the mid-hinge point, you do not want to have a good structures. Why? Now you have to imagine that you have very large structures. And then when you have a large structure, if you depend on the each point side, so what you're going to have is that there might be like, you might have this incident where it just close. Okay. So what we want is that another pivot point. So this is what we call as the dorsolateral hinge point. The dorsolateral hinge point is area of this page. So basically what you want is that one and then you want that one. So by having that one, you have, but in order to make sure, because of the hinge point again, the hinge points always have the structure, the wedges structures, right? So now you have all those wedges. Now, because of you have this one, the natural movement here and then and there. So basically you need what we call the apical constrictions. The apical constriction basically is the opposite force, so that to ensure that if you don't have any apical constriction, what happens that you're going to have a structure like this. You awkward and then you have that structure like this. You don't want a structure like this. You want to be like that. So meaning that the opposite structures, the opposite force must be applied to the structures. Then this one we call it the apical constriction. Where do we get this apical constriction? Because of this was given by all the epidermis or the rest of epidermis somewhere. The surface element. Right? So because you have to make this one is always connected to the element or with surface element. So when it tries to close, basically it tries to stretch the surface element. Because surface element is stretched, right? So for every reaction there will always be equal and opposite reactions. So it will hold the structures. So by giving the opposite structure to now become equal structures, then you can have that. So this is what we call it the primary relations. The primary one basically the difference between the primary, okay, you remember this diagram, and then you compare with this diagram. So this is what we call it the secondary relations. What happens that secondary relations is you will get the secondary relation basically somewhere in the caudal area in human or in fish. So what happens is that if you remember the shape of your spade, right? So this area, because it's large, then they have what we call the leverage of forming the lumen is the ordinary neuron with the lumen inside. But this one is because of it's too thick and then it's too small. They have no what we call it the leverage to form the structure like this. So what happens is that they form what we call the neural kit. The neural kit is basically, if you can imagine the structure that now these structures become bigger and bigger. So what happens is that you start to have to form the structure like this. So you form this, then you have neural kit in the middle. So what happens is that one point the neural kit start to move, form the structure like this, and then start to move. So now you have, so basically you can imagine you will have this, and then you want that. Okay? So this is the difference between primary and secondary. In the secondary, you are not involved any hinges systems. What you have is the neural kit. Alright. So in secondary, basically, you only have a flat structures and then opening, but the primary, straight away you have a lumen. Alright. So now you still have a lumen. But especially in the member caudal area, then why you need this one is because of you have a smaller neural plate, and it's not only smaller, but it's thicker compared to the caudal. Okay, right? Get it? So simple, right? Right. I think we finish within 1 hour. Right. So this is basically neural tube organization. So if you look at if you remember what we have at the end of the process is these structures. This structures alone is useless. Why? Because it only control information from top to bottom. Okay, that's all. But it will not have any effect on the side by side, left or right of your side. So what they want is that they have to connect the connections area. So this connection area was behind by neural crest cells. So these neural crest cells we form the dorsal root or the ventral root, and then you have ganglia or whatsoever. Now this one will become close to the whatever the nervous system sympathetic parasympathetic. Right? So this is basically, and then all those things is overlap within this area. Alright? So the gray area and the white area, and then from gray area and white area they will go to the tail or to the tail. Okay? So that is what happens. That is the connector to your body. But in the upper parts of your body, if you remember that you have a structure, the leaf structures, and then this is the neural tube, and then you have the opening somewhere. So this is what happens. This is what happens. In this region, basically, you are not going to have a complete closure of the neuron. Complete closure. Why you have no complete closure? One of the reasons is that these structures is being filled out with what we call it with the fluid. So with the fluid, then what happens is that you have some sort of like, now it become bigger size. So the first ventricle, basically what you have is that, so this is happen to the first ventricle, within the first ventricle. Now you have prosencephalon, you have encephalon, and then you have encephalon. So prosencephalon basically your inbrain over here, the midbrain, and then the forebrain. So the bigger one, the cerebellum, and then you have the what do you call it? No one. Cerebrum. You have the stem, brainstem, cerebellum, medulla oblongata. Okay? Right. So all those things. Right. Cerebrum. Right. So what happens is that there is a special structures. There is special structures that because of being filled up with the fluid. Okay. So this is the fluid. So what happens is that it will increase the volume. Not increase. Now what you have is only like, you know, like roti puri. The puri bread, you remember? Yes. You know why the puri bread is bigger, but somehow inside it is just air. Also, like your brain now. Meaning that you have no idea. No idea what I'm talking about, because doctor, I just saw your notes about 10 minutes ago. But bila ini notes pagi tadi, you download a new one this morning. Have you downloaded this one this morning? Or maybe that's the first note because you haven't got time to download from the maybe you are very busy, right? After all, your lecture is up until what time? Ali habis tadi? Was that good?
5 minit, 10.05.
10 minit. Okay? Very busy person. Okay? So it's only empty like a roti puri. If I said roti puri, everybody will remember okay, roti puri. So that's why you want a neuron to be connected. So that's why now if you know something, now you can like, now the neuron is connected. So basically it's just empty. But on top of that, all this emptiness, now you start to have the formations of all the pharma. So the pharma basically it become your optic pharma, your ears, okay? All the pharma will be connected to the midbrain or the cerebellum. So that's why your brain is somewhere this area. And your eyes is near to your brain, your ears also, your mouth, and so everything. most of the sensory, how many sensors you have?
5.
How many is near to your brain? One, two, what else? 3, 4. Which one is 5? But majority of the sense is near to your brain, right? That's why you need to think before you do something. Alright? But if it's not useless, then maybe look if your God. Our God put our brain somewhere in your body. Right? If it's not. Right? To me, that's a loss. Right? So this is what happens. So once you have by week 4, basically you have what we call the primary brain vessel. So you have the formations of the structures. So you get here 1, 2, 3, and then this structure is later on become is called the cerebellum. Okay, and then you can see now the cerebellum become. If you look at here, most of the structures develop somewhere from the process cerebellum. So here we come, and then cerebellum, here cerebellum. So this is what, right? So why we need? So if you look at in terms of the relations. So basically, what we have now, here is only this one can only happen one computer. So by doing 4, you need to have a brain. But your brain is not functioning yet. It's not functioning yet. It just like working to expand without nothing inside it. So you need to fill up the brain. You need to fill up all those the neuron. So the neuron can only find what happens is that what you want to know. How do you increase the numbers of neurons? You need the numbers of neurons very simply. It was to get a good boost of power. The boost of power can you get through the glucose, right? So you need to increase the glucose, but not too much, right? So I think just to show you this video, basically this is a good video. You just have to summarize.
Although in this video we're going to talk about neurulation. This is an embryology video. Now, neurulation is the process where the neural tube forms, and this is about week 3 to 4. And the neural tube is important because later it will form the brain, spinal cord, and meninges, as well as a part of the bones that surround it. Now, here is a cross-section of the embryo, and there are 3 important layers to it. These are the ectoderm, mesoderm, and endoderm, and they form early in development. And so the major event of the 3rd week of development is gastrulation. Gastrulation is basically where the 3 primary germ layers, the ectoderm, mesoderm, endoderm, form and start becoming tissues. So the embryo is like a ball. Cutting a cross-section, the cells of the embryo differentiate into 3 main cell lineage. The ectoderm, mesoderm, and endoderm. Again. So the ectoderm will then differentiate into other things and will essentially give rise to the nervous system and our skin. The mesoderm actually originates from the ectoderm. The mesoderm will form the connective tissue, and then it will also rise from bone, muscles, the urogenital organs, the aura, as well as the peritoneal lining from the cavity. The 3rd important germ layer is the endoderm, and this will give rise to the lining of the internal organs, such as the GIT and the lining of the airways. An important structure to know is the notochord, which actually induces neurulation, starts the process of neurulation. And it will then form later in life the nucleus pulposus of the internal surgical complex. So this is week 3, and by week 4 and 5, you end up with this structure. So To imagine what is happening, imagine the ectoderm folding around the endoderm and mesoderm. The endoderm itself becomes smaller and the mesoderm becomes larger. So from earlier, you have the ectoderm, which has overlapping, which makes sense because the ectoderm is the skin. The mesoderm in the center, which makes sense because it will form bone, muscles, and connective tissue. And you have the endoderm, which is small because it forms the lining of the GIT and the airways. Also, there is your notochord still hanging and will become part of the nucleus of the backbone, the nucleus of the process. During the process, you also see formation of other structures. The somites, which is part of the mesoderm essentially, and will form the bone, muscles, and tissue. And then there's also the neural tube, which comes off the ectoderm. And this, remember, will form the central nervous system, so it will form the brain and spinal cord, amongst many other things, the lineages. So this is actually the focus of the video, how the neural tube forms, and the process is called neurulation. So back to our first page, this is already week 3, and the process of neurulation is about to begin. Let's zoom into this area here. So here is your endoderm, your ectoderm blue, and your mesoderm red. By the end of the 3rd week, the lateral edges of the ectoderm here become more elevated and will form the neural fold. The depressed mid-region is called the neural groove. This whole layer now is actually called the neural plate of the ectoderm. Now we are looking at this from on, but let's take a look at what it looks like from the top. So we're looking at it just from the top. So we are looking at the top of the neural plate. Remember, the process of neurulation gives rise to the brain and the spinal cord. And from the top of the neural plate, you have the cranial, which is the head, and the caudal, which is the tail end. Neurulation advances both cranially and caudally. So it starts from the mid-region. So the end of neurulation, the cranial end, will eventually give rise to the brain. And then going caudally will be the spinal cord. Remember, at week 3, the neural plate gives rise to the neural fold at either end, forming the depression in the midline called the neural groove. Eventually, the neural folds will approach each other and fuse, thus converting the neural plate essentially into the neural tube. And this fusion process typically begins in the middle and advances both cranially and caudally. So neurulation advances both cranially and caudally. Looking at it from head-on again, so from the front, looking at it from a different view, what we are seeing are the neural folds meeting, fusing together, and it will form the neural tube as a result. The outer part of the ectoderm will begin moving down and surround the endoderm, the mesoderm, as we talked about. So by the end of week 4, you have the neural tube form, which again will form the central nervous system. As a neural tube forms, some of the ectodermal cells from the tube migrate to form several layers of cells called the neural crest. The neural crest will give rise to structures that work very closely with the central nervous system. And there's a lot, but they include the peripheral nervous system, spinal and cranial nerve, and the ganglia, the autonomic nervous system ganglia, some of the meninges as well. Of course, the remaining ectodermal forms here. Here is a notochord, which actually stimulates the whole neurulation process. Here is the endoderm, which will form the inner mucosal lining of that area. So let's look at the whole process from the top again, focusing on the neural plate. By week 4, you have something that looks like this. From the cranial to the caudal, 4 segments of the neural tube. It's essentially 4. Neural folds and fuse. because the neural tube gives rise to a single nervous system, you can think of the neural tube in terms of sections. So during the rest of the embryonic development, when the neural tube forms, the spinal cord
Macam
becomes
pet.
growing development.
Macam pet.
So
Kepala wanita.
the mesencephalon becomes the midbrain, and
Semici.
the prosencephalon is cerebral.
Itu je aku terbayang tu tadi.
Hope this video makes sense. It's quite extreme. Thank you for
Neural plate. Neural fold. Pula tertidur.
Okay. Later on, I will try to share this with you all. Okay? If you want it. If you don't want it,
Want.
just leave it. Okay, alright. Okay. So any questions? Before we end the class? Any questions?
Balik dulu lah.